Why, hello there. Would you like to see a magic trick? Uh-oh, 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 uh-oh. No! My perfectly sorted deck of cards. How? What do I do? One method we could use to sort this list is bubble sort. It's a fairly intuitive method, but as you'll see, it has some drawbacks. To begin, we want to find the greatest possible item in this list here. So we're going to start at the first index, and that's a jack. And then we're going to increment to the next index, which is a 5. And we're going to check to see if this 5 is greater than the jack. In this case, it's not, so this is still our max value. Then we're going to keep incrementing over. Is it greater? No, 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 no. And this continues for the whole list. So what happens after that is that the last element and this greatest element here switch places. So now all we know after this first pass is that the jack is in the correct spot. So then we repeat this process. So we check for our ace. Is it the greatest compared to this? No, this is the greatest. Then we compare it to this. Now this is the greatest. Compared to this 2. Compare to this 10. Compare to the 5. Compare to the 7. Compare to the 3. Compare to the 8. And we don't compare it against this jack. Each time, the amount we compare it to shrinks by which increment we're on. So because this is now the greatest, we swap places. And then go back to the beginning. So this process repeats. Is the greatest, so we swap it. 6, that's 5. And you'll notice there's a lot of redundancy happening here with these comparisons. I'm actually going to swap for this 5, so that'd be a greater than or equal to sign, and that's so that this remains a stable algorithm, where the elements remain their relative position to one another. That is how you sort a list using bubble sort. A general issue with comparison-based algorithms is that they have a best case time complexity of O of n log n, which still isn't great. To solve this, counting sort arose as one of many non-comparison-based sorting algorithms, which is to say elements do not get compared to the elements next to them or any neighboring element. Counting sort begins by getting the range of possible numbers in the list. In this case, we already know the range because each suit of cards has 13 unique variations. So the next step is going to be creating an array, an empty array of size 13, so we can store the count of each of those 13 cards. The index will represent the number, and the value will represent the count. To see what this looks like, I've created our empty array, and now we're going to iterate through this list, count up the occurrences. So we're going to start, and that's 8. So we're going to go to the 8th index, which is marked as 7, and we're going to set that to 1. Then we're going to increment over, and that's a king, so that's going to be our final index, and we're going to increment that by 1. Then we're going to increment over to 7, and that's marked as 6 here, so that also becomes 1. We go to 6, add that up. We go to queen, so we're going to add 1 there. And then we're going to add a second to queen, so that now becomes 2. And then the rest can just become 0. And now this array represents our data set of cards, but just mapped to their values. The next step is using our counts array to get the new positions for each number in the final sorted array. We can do this by creating a new array, also of size 13. Each item in this array will be the sum of all preceding items in the count array. So what this looks like is that 0, this index here, will be the sum of all preceding items in the counts array, which is just 0, because nothing comes before it. Then position 1 here will be 1, because it's the sum of 0. This will stay the case, because nothing's being added. Then for position 4 here, we're going to add this 1 here, so this becomes 2. Then for 5 here, we're also adding another 1. For 6, we're adding another 1. For 7, we're adding another 1. For 8, we're adding another 1. This stays the same because these are just zeros. And then for 11 here, or for 12 here, we're going to add this 2 from the 11, so that becomes 8. Now that we have our positions, we've essentially created a map for where to place each of these cards. So now the next step is going to be to create a final array of the length of our original one, as represented by these indexes here. And this is going to be where our final sorted output goes. And then we can increment from the beginning of our unsorted array. We can look at the card, and then we can find its value in the map here. So that's going to be position 7. So we're going to go to 5 over here, and that's its final position. We're then going to increment to the king. Oh, and after this card goes here, you have to increment this count here by 1, so that if there's a second card, it comes right after it. But now we've incremented to the king, so then we find the king's position, which is the last one, so we know it goes in position 8 of our new array. Then we go to the 7 here, we find it in the key, so that's going to go to position 4 of our new array. And now our array is completely sorted in its final order. Perhaps you want to apply the speed of counting sort to a larger range of numbers. In that case, you'll want to use Radix sort. The underlying principle of Radix sort is breaking each number into its individual digits or characters, and sorting by each character until the whole number is sorted. I'll be showing Radix sort least significant digit, which starts with the smallest place value instead of the greatest. You can just imagine that these cards would be a base 13 number system. This would be your 1's place, this would be your 13th place, and this would be your 169th place. Radix sort begins by getting the longest number. The length of this number will determine the number of passes necessary to sort. In our case, the longest number is 3 cards. That appears a few times. We will then create an array to store the first place value for each number in the original array. So what that means is that we would create an array where we basically just temporarily ignore all these cards, so that we're only looking at the first place value. This array up here will essentially act as our keys. Now we can call our counting sort function to get the positions where our number will go. So I've chosen to represent our counting sort function as this jar of tomato sauce here. Oh wait, no, this is, right. As this mustard bottle here called get positions. And this will get us our positions array. All right, so our get positions function has finished running, and we essentially ran through counting sort with this entire array up here. So now we have the final indexes for each of these cards up here. The only difference is that this time, now when we're incrementing, instead of moving just this card here, or just this card here, we're going to move the entire number to that position. This jack here, we know is going in position 7. So we're going to move this jack and the cards that come after it all up to that spot there. And then we're going to increment over to the 3 here. We're going to find its place here, which is at position 3. So we're going to move this card, but also its associated card, which is a 4. Then we're and that would be the first pass. So essentially what we have to do is run through that entire procedure again for each place value. So we have this function here represented by the tomato sauce jar called getNextDigit. And we would call that function on this entire, this would be our new input. So we call this function to get the second position. So that would be our 3, 4, 8, 4, 9, 5, 10, ace, 10, 2. So we would separate those cards out, and then we would call get positions, but instead of using the this first rows are keys, we're now using the second rows are keys. So it's a new set of indexes, and we're moving the entire number to that index. So I'll speed ahead and you can watch that for yourself. Alright, as you can see, again, it doesn't look sorted until you look at the second place value, where everything is neatly sorted. Yeah, so ace, 2, 3, 4, 4, 5, 8, 9, 10, 10. It's a bit hard to imagine what this means for cards, but essentially if this is our ones place value, it's not so important, so the fact that it's now out of order is okay, because these are bigger numbers anyway. So in the same way that 51 is a greater number than 49, because you're not looking at the ones place value, you slowly work your way up to the greatest place value. So then we would call this function again, getNextDigit. You'd call it again for this final row here. Alright, so again, it may not be initially clear how these are sorted, but as you can see, these are all your smaller numbers because they don't have that third place value. And these are your larger numbers because they do have that third place value. But you'll also notice that they maintain that order from earlier. So it goes 2, 4, 5, 8, 10. So you know that these are all correctly sorted. And here with the second row here, you can see that these two, which are both in the 5's place value, the 10 is coming after the 9 in the second place value. So they've maintained their order. And that's because counting sort is a stable algorithm, so you can run it recursively and it'll maintain their relative positions, which is how Radix sort works. Leave the grunts in. So just to go into a bit more detail about each algorithm, bubble sort has a time complexity of O of n squared, and that's the case for the best, worst, and average. Counting sort is significantly faster. Its time complexity is O of n plus r being the range, and that's also the case for the best, worst, and average. So while bubble sort was a quadratic function, counting sort scales linearly with the size of the data sets. The drawbacks are that it takes up a lot more space to create all the temporary buckets, and it's only efficient for a small range of numbers, like 0 to 10. It also only works for positive integers, because it uses the indexes and you can't have a negative or floating point index. Radix sort is able to solve the issue with the range by going digit by digit, Its time complexity is O of k multiplied by n plus b, k being the length of the number, and b is the base of the number. So you can think of this as being our counting sort function, except that instead of range, it's now base. And it's being called for each digit. And this is also the case for the best, worst, and average. So it's actually very fast. It's almost as fast as counting sort, assuming your numbers are consistent in length and not too long. The drawbacks are that there's a lot of redundant operations if you're not using fixed length numbers. So you can imagine if you had a number that was 1 digit versus a number that's 20 digits, you're going to have a lot of redundant operations on that 1-digit number. And also because it's using counting sort as a subroutine, it can also only sort positive integers, which limits its use case. Now I can finally show you my trick. Perfectly sorted change.